Trying to show that a very popular number theory function is multiplicative, and I'm underlining the word multiplicative because this is the definition of what it means for something to be multiplicative. If the two inputs are coprime or relatively prime, then it splits like this. Okay, this is literally the underlying pieces are equivalent. Okay, now you guys are familiar with this symbol here. This means it's not a point in the plane. It stands for the greatest common divisor. And just a quick example, let's do something like 21 and 8, something simple. Now notice that 21 has a prime factorization of 3 times 7, and 8 is 2 cubed, which is its prime factorization. So they share no common factors, ergo their greatest common divisor is 1. Okay, so that's what this symbol means. Okay, some people will put GCD out front, or highest common factor, HCF, I think. So anyway, we want to show this is multiplicative. And here's your definition of the Möbius function. This is called mu, the symbol mu. And now, it essentially is a symbolic way of distinguishing between square-free integers. Now, notice right here, if p squared divides any integer, this little vertical bar means divides. If p squared is a factor of n, then it's not a square-free number. It contains, like, for example, 50 would be an example of a number like this. 2 times 5 squared, I'll just write it off to the side. I'll just make it like a u, folks, sorry. Mu at 50 would be equal to 0. Okay, because 5 squared divides 50. 5 squared is clearly a divisor of 50, right? Okay. Now down here, this piece right here, it's not square. There's no squares in this because all of these are distinct primes. This is kind of cumbersome, but there's t prime factors. Each of them are distinct. T would be a natural number, 1, 2, 3, 4, 5, 6, and so on, a positive integer. So you see, these numbers, let me just write SF, if you'll tolerate that, square free. Okay. Not sugar-free, but square-free. Okay? And so it's important to have this kind of notation. It turns out you wouldn't know this a priori. But let's continue with the proof. Okay, case 1 is the simplest. If either of the inputs are divisible by some prime squared, okay, you're going to get, you know right off that mu at AB is equal to 0, right? Because one of the factors is divisible by a, let me put a dot there. One of the factors, one or both of the factors is divisible by a prime squared, okay? But notice this is equal to mu. I mean, it's what a lot of people would pretentiously call trivial, okay? Because these are manifestly equal to 0 since, you know, each one of these is 0, right? This one, you got to say one more word here because if p squared divides A, it's going to divide AB. If p squared divides B, it's also going to divide AB. So therefore, so this is trivial right here, right, folks? I'll quit talking about that. Now let's go to the one that's slightly more interesting. And notice, y'all, there are two cases. You're either square free or you're not square free, right? Okay. Now, case 2, you are square free because we're saying that p squared does not divide A, and it's both, right? This is kind of like De Morgan's law stuff here, or and negation and all that. Now, so, but anyway, we would have to go ahead and express A like this, okay? And both P and Q these are primes. P, Qs are primes, right? Just, oops, let me come back here. The P's and the Q's, they're prime, okay? And they are distinct by the, why are they distinct, folks? It's because AB is congruent to 1, right? So let me write this. This will be easier to say. Our given condition, sometimes you forget to appeal to some important things. I almost did then. But since AB are relatively prime, they have no common factors. Remember, that was the original condition for multiplicative, a condition for to show something's multiplicative, the inputs have to be relatively prime. So if A and B are equal to 1, if A and B are relatively prime, that would imply that PI, none of the PIs equal to any of, we'll call them, what do you want to call them, QJs? Okay. Right, folks, and that's an important condition here. Okay, if you didn't have the relatively prime going on here, some of the P's might equal to some of the Q's is all I'm trying to say right here. But this implies that P sub I never equals Q sub J for the appropriate ranges here, for the C and D ranges here. Okay, so here we go. So it's clear that mu at A is equal to -1 to the C based on the definition, right here, folks. Okay, I'm just using the definition, used a different letter here, okay? And the same for B. Here we got D, but the letters are in our face kind of here, but anyway, this much is clear. Now mu at AB would just be equal, since they're all distinct, you just add them up, right? -1. But what is this? By the simple property that you learn in middle school of exponents, this is equal to -1 raised to the C times -1 raised to the D, right? That's cool. But what is that? That's mu at A times mu at B, just from the definitions. Okay, and y'all, this makes it QED time. That's a B there, sorry. So QED, get a little more space here. So we're done, y'all. And again, y'all, basic laws of exponents. Let's see, what was the law of exponents that we actually used here? Something like this. If you have A, B, I'll use uppercase here. By the commutativity property, how many people can still pronounce that word? This is equal to A to the N times B to the N, which is all we did. This is basic, like middle school level, maybe even some advanced, maybe in secondary school, I don't know. But this is true just simply because A and B commute. You can just huddle them up all together and get this, right? And that's the property that we used to prove this result, just a basic result from algebra, properties of exponents. But anyway, folks, we are done. We proved what we set out to prove. 2 cases. One case was real easy. Other cases, just a matter of writing down the prime factorizations and appealing to the fact that the 2 inputs were co-prime. Okay, that's all.